attention and vision. Although prepared for the idea of attention by Badanov, although introduced for an encoder-decoder sequence-to-sequence problem in natural language processing, people quickly applied this idea to vision. Well, it's a bit confusing, I mean, because if you want to apply this idea to a vision problem, you need a sequence-to-sequence problem, right? But the first problem they applied this to was image captioning. You remember show and tell. We have covered show and tell. Actually, we have done live codes on show and tell. We have gone over the training steps of show and tell and results, remember? And these guys come up with this clever title, which is show, attend, and tell, indicating that show was the encoder part, tell was the decoder part, and in between we have this attention layer, and let's call that in the title attend. So this is show, attend, and tell. But the thing is, in the NLP version, Baldanov's paper, there's a recurrent encoder, the attention layer, and the recurrent decoder, right? But in our case, we have a CNN encoder. We have the attention layer in between somehow, and we have the recurrent decoder. Well, okay, recurrent decoder is okay, but the CNN encoder part does not take a sequence as the input. It takes an image. So how come this is a sequence-to-sequence problem? Because for the attention model to work, it should be a sequence problem. Remember, that was what we said in the previous hour. So this is the first time that we are going to be treating the image concept not as a fixed length signal, but a sequence of patches or dimensions or, I don't know, features. We are going to do this. So do you remember the introduction lecture, the first week? We were talking about what is a sequence and what is not a sequence. And we said that image was not a sequence because it was a fixed length signal, blah, blah. I said that's why CNNs were good with them. Then a few slides later, I said that image can be thought and treated as a sequence as well. But that was the concept of attention, and it was the concept of the following weeks and etc. And we've arrived there. So we are talking about the model of attention, so where the images are sequences. So how? So this is it, guys. This is the mechanism. They've used the same figure types as the show and tell. So in show, attend, and tell, what you do is you have the input, you feed it to simply a CNN, which is VGG in this case, and you take the output of the last convolutional layer. If you remember, in show and tell, the previous version where there was no attention, they have taken the output of the fully connected layers, not the convolutional layers. So there's the convolutional layers and the fully connected layers in VGG. They have taken the fully connected layer before the softmax layer. I mean, not before, because before the softmax layer, there's a fully connection layer that gives 10,000 categories output, but before that there's a 4,000 something fully connected layer. Remember VGG? That was what show and tell used. In show, attend, and tell, it is not the fully connected layers, the final convolutional layer. Why we are going to get there? And in the final convolutional layer, what we have is some number of filters, which is 196 in this case, 196 filters. Each of them representing a concept of the image. Actually, they can be thought of a sequence, and that's what they did in this study. And they feed this sequence of feature images into the RNN, and there is an attention layer in between, which is fundamentally and mathematically the same attention mechanism we have seen in the previous example of Badanov. So the sequence in this example will be not in the token dimension or the time dimension. It will be in the feature dimension, feature type dimension, different types of filter. Each filter describes a different abstract feature. In this abstract feature space, we create a sequence of signals that represent the input image. Quite strange, but we'll get there. So this is a figure from this guy. It explains that this guy explains the study very well and created their own figures. So we have the image, we have the VGG, we have the last convolutional layer of the VGG, which is 196 times 512. So it was not 196. I was wrong. It was 512 filters. Okay. So it's the number of filters. The number of filters. So at the last convolutional layer, I have 14 by 14 by 512 filters. Since it's a two-dimensional convolutional neural network, as you convolve and cool, the image is downsampled into 14 by 14 representation from 224 by 224, because the input of the VGG was 224, if you remember. So there are convolutions and pullings and convolution and pullings. It becomes 14 by 14. And we have 512 of them. So let's say 512, the number of filters is D. And the number of vectors that represent different parts of the image is 14 by 14, which is 196. So actually, I can create a set of vectors which has different vectors. L is here 196 vectors. So each vector here will be 512 length, right? So it's a sequence of the positions. Maybe in the like a minute ago, it was a sequence of the features. I said wrong. This is a sequence of the locations in the image. So the first location will be, maybe I should draw it. So this is the input image. This is the input image. So in the final layer, it is being cut into 14 pieces. 14 pieces. So this will be representing A1, right? However, there are many filters going on, which is the number of D, which is this case 512. So for representing this part, this region of the image, I'm using D number of activations, number of different filters. So D number of filters, D number of filters, D number of filters for this part, D number of filters for this part. So this is a sequence. So in this is the dimension of the space, not time. The positions, the locations of the input signal. So what I do is I'm taking an average of these vectors. Alpha is the weighted average. I'm creating the context vector Z here. I'm going to call this Z. Okay. And I'm going to concatenate it with the hidden state of the decoder and feed it there. So that's the idea. I'm going to get into the very details of it. Don't worry, I'm trying to make a top to bottom approach. So that's how the sequence dimension is introduced in this image captioning problem, because the image was not a sequence. So how am I going to treat the image signal as a sequence is like this. So this is a sequence of different regions of the image. Each token, each region is represented by 512 the number of filter activations. And to create the attention model, I need to take the hidden states of the, because these are like the hidden states of these regions. It's a intransparent representation of that region. I weight them, I create a context vector and feed it. And the context vector will change for each image. So for each word that is created at the output. Okay, let me not confuse you more. Let me continue because we are going to do it. So features are extracted from a lower convolutional layer, not the fully connected layers. So the output is 14 by 14. So L is 14 by 14, 196, and the number of filters is 512. The feature map of the fourth convolution layer before max pooling in image pre-trained VGNet. You could use different networks as well, but they've chosen to use this. Most probably they have done experiments on what part to use, which part is the best, and they've come up with this result. Okay, so I come back to my figure. That's the figure. Let's go and try to understand this figure in more detail. So these L figures are like the annotation vectors, the hidden states of that sequence, and they represent different regions in the image. So what I do is I encode this, I have the attention mechanism, and I feed it to the decoder. Now I want to remind you the actual show and tell. In actual show and tell, we didn't have the attention layer. Instead, what we had was the decoder, but not what we had was the encoder, but not the convolutional output, but the fully connected output. So it is like the attention layer replaced the fully connected layers of the BGG, which makes me think that attention layer is a layer that helps me to focus on the related part of the image. Okay, maybe the fully connected layers were doing that for me in a less efficient way. So we come to that discussion again, the one we did in the final parts of the previous hour. Anything, artificial neural networks, fully connected layers, what they do is they focus on a part and they do not focus on the rest of the signal. That's what their job is. That was what fully connected layers were doing it for us in the previous version, show and tell. Instead, we have designed this attention mechanism to make it more efficiently. And it's going to do that for us. Let's see how it does. So I'm going to focus on this part only now, guys. So what I do is I have these different regions represented in d-dimensional filters, 512. And I calculate the weighted average of them to get the context vector. So how do I obtain the alphas? The alphas are obtained by using a function, guys. This function, okay? Because alpha is obtained from this value E, and that value E is obtained with a function, which is actually a fully connected layer of these values and the S. What was S? Do you remember what was S? The decoder hidden state. Remember in the previous version, in the previous hour, let me get back to that slides. The weights were calculated as a function of, it was the dot product, of the decoder hidden state and the encoder hidden state. It is the same, guys. It is nothing different. The weights are calculated before normalization because this is softmax normalization as a function of these two. In the previous Badanos version, it was a dot product. In this version, actually, it is a weight matrix, like a fully connected layer. So there's a layer there that you can learn. Do you remember what we said? It could be a dot product, or it could be something, you could have a fully connected layer, a network, a multi-layered perceptron to learn that. So the input is the concatenated decoder and the encoder hidden states. AI is the encoder hidden state. And the decoder hidden states, all the encoder hidden states plus that moment's hidden states, decoder hidden state. And you have this score function. Then you normalize it. That's the weight. So actually, the idea is the same. You are using the encoder hidden states, all of them, and the current decoder hidden state to calculate a score function, which you normalize by softmax, and you obtain this. Okay? So in a way, when you define what the sequence is for this input type, then it's the same. The attention is the same. You calculate a weight using the input hidden states and the decoder's current hidden state. When you have these weights, all you have to do is make the weighted average, calculate the context vector, and feed it to the decoder concatenated with the decoder's previous hidden state. Any questions? They are complex ideas, but if you get used to them, they're not that complex. Okay, so I strongly recommend you visit this website. Anyways, let me get to where I was. So that was the idea. That was how we've calculated the context vector, very similar to the Bahdanaz model. So in this way, we have 116 positions in the sequence because the sequence dimension is different regions of the image. And the feature of each position is represented by 512 filter activations. And these vectors are weighted with these weights that we calculated using these functions to create the current context vector. Good. So while we are calculating the context vector, we are using the alphas, right? If it is the weighted average of all of them, we are using all of them. At this point, these guys show attendant alpha. They define two types of attention, just like global and local attention, Manning defined on Bahdanaz model. These guys define two types of attention, hard or soft attention. So hard attention is if alpha is a one-hot vector, which means one alpha is 1, the others are 0. So it is like you have a softmax, you choose the maximum of them as 1 and the rest to be 0. Or you get the softmax, which is the soft attention. With the values are a distribution of values between zeros and ones, which add up to 0. So if you use the actual output of the softmax, it is soft attention. If you use the output of the softmax such that the maximum value is 1 and the others are 0, that's called hard attention. Hard attention is you're only focusing only one region in the image. Soft attention is while you're creating the next output for the decoder, you are kind of making an average of the regions in a weighted manner where the weights are calculated by the softmax. Okay, they try both of them. And to understand their study, what they do is they visualize these alphas, guys, because these alphas are the weights of each region, right? By using these alphas for each region, I can create a kind of a heat map over the image, right? So for each location I, 14 by 14 locations, the mechanism generates a positive weight, which is the output of the softmax. It can be interpreted either as the probability that location I is the right place to focus for producing the next word, or the relative importance, I can say, to give to the location I when we're blending all eyes together. So if I'm going to focus on one part only, the hard attention, it will be that part only. If I'm going to make a combination of them, it is that alpha will be how important that part to me when I'm creating the next part. And the best way to understand is to visualize these alphas. So the weight of alpha for each annotation A, annotation is the regional filter activations. So this function is actually calculated by a multi-layer perceptron. So there's a fully connected layer for each of them. How do I learn them? Think of this as a computational graph, complex computational graph you created in PyTorch. It will automatically learn during backpropagation. That was what they did. So they did not take the dot product. They somehow created a multi-layered perceptron, a fully connected, a linear layer, so that it would learn how to create those weights during training. Remember, this was a possibility when we were talking about the basic plain model of recurrent model of attention in the previous hour. Okay, so this function is a multi-layered perceptron, a linear layer. So, and we create the context vector. The rest is the same. We feed that context vector. So what if we depict alpha at a given instant? I'm sure when people talk about this attention, they all have these figures. And if you already know what attention was, it will be trivial to you. But if you didn't know what visual attention is, this is the first time you're seeing it. So I'm feeding A. And when I'm feeding A, I'm feeding the image to VGG. Okay. I have some hidden states. So this is the first state. At the first state, as an output, I've created a S0 or S1. By using S1 and the actuations for each region, I've calculated the score function. By using the score function, I've calculated either a soft attention or a hard attention. If it's a hard attention, one alpha will be 1, the others will be 0. If it's a soft attention, these will be values between 0s and 1, which add up to 0, like a probability mass function. So these are the regions that represent 14 by 14 grid on the image. So if it is hard attention, it will be one region in the 14 by 14 image. If it is soft attention, it will be the additional alphas all over the image, belonging to different regions. So if I visualize them, I'm sorry. I think I'm okay. So it will be representing these parts on the image. So when I say A, it is here. Doesn't mean much. When I say bird, look at the soft attention. The alphas are aligned such that they cover the bird. When I say flying, they also cover the bird. When I say flying over, they also cover the bird and the bottom, because over relates to bottom. The body, and let's come to this part of the image, body of water. It is what the sea is all about. So, I'm really sorry. So this alpha is actually a very nice depiction of what parts of the image is related to the current hidden state of the decoder, hence the current output of the decoder is. And if it's soft attention, it's a bunch of regions. It's hard attention, it's a single region. That's it. That's all what the paper is. And it's, if you build it on top of the encoder-decoder attention model that we inherit from Badanow, that's it. That was all the idea. And it's a very famous paper. Let's go over the results, and it will give us an insight about the study. So a woman is throwing a frisbee in the park. This is soft attention. A very nice, successful results. So in these results, coming from their paper, I'm going to be showing only soft attention. So a dog is standing on the hard wave flow. Dog, this just pinpointed. A stop sign, well, quite stronger for soft attention. It looks like hard attention. So successful results still. A little girl, so at girl we have the divinity light over the head of the girl. A group of people. A giraffe is standing in a forest with trees everywhere, but the giraffe is white. So it means alphas around these regions are stronger. Alphas that fall to the regions where I have the giraffe is lower, I think say. So these are the successful results. So not so successful results. Well, I thought of doing a similar experiment to show and tell. I didn't have time to do it, and I didn't have resources to do it. Actually, we have a GPU, but we are running the GPU for some reason, so I couldn't do it. Sorry. Maybe you can do it. There are very nice codes for show and tell in the internet that you can directly download and just work on. So a large white bird standing in a forest. Apparently, the mechanism thought that this is a bird because it looks like a bird when two giraffes are, I don't know, combined. And it thinks that this is a bird. And it just puts the alphas around that region. Well, it's not successful, but in a way, it is successful because it thinks that this is a bird, and it points that it's a word. So the mechanism is working correctly, but the result is not successful. A woman holding a clock in their hand. So this is the arm. Maybe the image thought that this was the extension of the arm, and this is a big clock. But not bad, because at least without the alphas depicting on the image, I would have difficulty to understand why this caption was created as a woman holding a clock in her hands. But now I understand it, because I'm totally sure the mechanism thought that this was a clock, because for the word clock, the alphas were very stronger in this part. They were stronger in this part as well, so it's not working very correct, but this gives us an insight. So attention is, what this example shows us this, actually a mechanism to make the focus of the encoder-decoder part, between the encoder-decoder part, more transparent. We can understand what's going on. A man wearing a hat and a hat on a skateboard. Well, definitely not a good translation. And when you try to understand where the skateboard is, it's quite distracted. So this didn't work out. This didn't work out. Not so successfully. A person is standing on a beach with a surfboard. So the surfboard is correct, but the guy is not standing on a beach. It's near the beach, so not so successful. I would say that. A woman is sitting at a table with a large pizza. Apparently, we had many pizzas on the training set, but we didn't have this street food. But in the end, the food is strong for the decoder hidden state that created the word pizza, right? A man is talking on his cell phone while other man watches. Well, the sandwich is mistaken for a cell phone, but we have this watch of the women also strong. So not a good one. Okay, so if we look at the differences, this is show and tell, this is show attend and tell. This was using a CNN where the output of the fully connected layers were used. In this one, we used the output of the convolutional layers. The fully connected layers were replaced by the attention layer, and the LSTM used the attention context vector concatenated to its decoder hidden states so that we have the mechanism of attention in it. So that's how we applied the same model to a sequence creation problem. And it was even not a many-to-many problem, guys. It was a one-to-many problem, because if you think of the image as a one, let me check it out, as a one. So this can this be applied to different multimedia problems? Apparently, and there are many problems that it hadn't been applied to yet, but you can. So to sum up the recurrent model of attention, because we are going to finish our business with the recurrent model of attention now. In the recurrent model of attention, also referred to as the Badanov attention, because they were the guys, I mean, Badanov was the first author who applied the idea of attention into recurrent encoder-decoder models. The model does not attempt to encode a whole input sentence into a single fixed length vector, but instead it encodes the input sentence into a sequence of words vectors and chooses a subset of these vectors. The sequence of vectors are the hidden states of the encoder. And a subset of vectors adaptively while decoding the translation. We say adaptively because while it's creating the weighted sum of the hidden states of the encoders, it always takes into consideration of the current decoder hidden states when calculating those weights. So that's the adaptively part. Okay, Badanov attention work because the one thing that we have gone over in show attend and tell, it was also the Badanov attention applied to vision only. It was the same idea. I mean, maybe the alignment vectors, the weights were not calculated by dot products, but it was calculated by a linear layer. Doesn't matter. I mean, you're learning it or you're calculating it deterministically. It doesn't matter. What you're doing is you're calculating alignment between the decoder hidden state to the old encoder hidden states, and you're creating a weight out of it, and you're weighting the encoder hidden state to feed it to the decoder hidden state, and you call it the context vector. This is called the Badanov attention. Okay. So various forms of this recurrent model of attention were proposed and is still being used today in iterate, in time series problems, and to make an analysis of time series problems. So RNNs coupled with attention seems to have solved a long pending problem in NLP, which is modeling learned-term dependencies. However, this changed in 2017 by a team at Google when they proposed the idea of transformers with a new form of attention. At this point, I'm going to finish my business with the recurrent model of attention, but please know that in your projects, if you're doing a one-to-many or many-to-many problem, you can always use attention, the recurrent model of attention, to visualize what the focus is in your sequence creation and do it. Without doing that, it would be impossible for you to understand how you're going with the problem. Are you being able to train the problem more, etc.? Okay, so if you're creating a sequence, there's always a way to use the recurrent model of attention. Okay, now at this point, we're going to talk about a different type of attention. In 2017, this Google's paper was called "Attention is All You Need." So you may think that it was the Badanow attention that has been applied to anywhere, but it was a different type of attention. They claimed that attention was all that was needed to encode sequences. And they even said that we didn't need recurrent models for encoding. So the type of attention they proposed was different than the recurrent encoder-encoder-based recurrent model of attention, the ED-based recurrent model of attention of Badanow proposed. It was a different type. So I'm going to give a break here. In the next hour, I'm going to talk about this new model of attention, but I'm going to get your questions first. Any questions about the Badanow attention applied to vision? No?